Right. Good morning, everybody. Thanks for being here this week's Rubin Science Assembly. I'm going to get us started, and then today's presentation will be from the SNAPS broker. For announcements, we've got Rubin Observatory has revealed over 11,000 new asteroids. So you can find the press release here. And also, when Rubin releases asteroids, they go to the Minor Planet Center. So that is the place to go to get that kind of data. A little bit of an older announcement, alerts are flowing and they have been since the night of February 24th. Alerts are publicly accessible. You can learn more at rubinobservatory.org or by visiting promptproducts.lsst.io, which is our prompt products technical documentation, or read the press release all about our first alerts. Looking towards the rest of this year, we're going to have the Rubin Data Academy coming up in June, the week of June 22nd. This is fully virtual and it's always held the week after the summer AAS, and its purpose is to mostly just sort of get students ready to do their summer projects on Rubin, but it's also a nice concentrated week of tutorials if you want to kickstart your own Rubin research. Later in the summer, the week of July 27th, we'll be hosting the Rubin Community Workshop at Slack in Menlo Park. The next deadline, like the next relevant deadline for that, is coming up May 11th. That's the booking deadline for the Slack guest house if you want to stay on campus at Slack. And then some of the following deadlines, June 15th is when the alternative hotels bookings deadlines are. And then June 22nd is our registration deadline, unless we reach capacity before that. You can find everything and all the registration links at project.lsst.org/meetings/Rubin 2026. Looking at our upcoming Rubin Science Assemblies, this is we're coming to the end of our series on broker presentations. Next week, we're going to have a presentation titled Early Preparation for LSST Chem and Data Preview 2. This will take you through two tutorials, one that shows you how to visualize the LSST Chem focal plane, and another one that shows you how to visualize the visits and the deep coad tracks that will be coming out with Data Preview 2. So it's metadata only, but it will help you a bit prepare for Data Preview 2, which is expected later this year. And then following week is going to be a presentation from Leanne Guy on early science. And that's going to be one presentation, then also a Q&A. So if you have questions about how the early science program is going, definitely consider attending that. Looking forward to, after the Rubin Community Workshop, also at Slack, there's going to be a KaiPak workshop, Rubin 2036 Opportunities for Discovery. So if you're already thinking about what to do after Rubin starts and finishes, you might want to stick around after the RCW and attend that meeting. Their registration deadline is June 1st. Then further in the fall, LSST at Europe will be in September, and the next LSST at Latam will be in November. As a reminder, you have a users committee. They actually met this week. They had one of their twice annual meetings on Monday morning, and so they're right now preparing their 2026A report, which goes straight to the director. So if you have comments or feedback about the Rubin data products or the science platform, definitely drop them a message or use their Google form to send them some feedback so they can get that into their 2026A report. Another regular reminder that the Link Frameworks team holds their tech talks and their drop-in sessions immediately after this session. And you can always drop in on them, learn more about the projects that they're working on, the software that they're building, and how you can use it. And now just a bit of an alerts and brokers primer before we get started with today's broker presentation. So of all the data products that Rubin is going to release, you've got the annual data release that come out on a yearly timescale, and then you have the prompt products that are near real-time process data released within minutes to days. And of the prompt products, there are the alerts, which go out within minutes, the catalogs, which get updated on a 24-hour time scale, and then the prompt images, which do have an 80-hour embargo, but then they are released to data rights holders after that. And so today, all the brokers work with alerts. Alerts are distributed to brokers, not to individual people. And later in the future, once the LSST alert stream is at working at full capacity, you can expect up to 7 million alerts per night that do go to the brokers. And so alerts and brokers together are like a community fountain where everyone can come and do their time domain science in real time. What is an alert even? One alert is issued for each difference image source that's detected with a signal to noise ratio greater than 5. So a new science image comes in, subtract off a template that's an older image to make the difference image. Then you run source detection on that difference image. And every source that's detected, whether it's a positive or negative, so whether that particular source increased or decreased in brightness between the science and the template, so long as that signal to noise ratio greater than 5, it gets detected and alert is produced. The alert itself is just a machine readable file that contains data for the detected source. So it's coordinates, measurements like the magnitude, observational metadata like the date, the time, and the filter. You also get the history of past detections up to 12 months. So the light curve comes with the alert. And then also very small image cutouts are included. Alerts are a completely public data product. And as I mentioned before, they're streamed to brokers. The brokers are independent software systems that process and serve alerts to the science community, but they do more than that. They add value to the alerts, they filter them, cross-match, they do photometric classification, and then they also offer data access services to users, either through web-based user interfaces or API clients, that kind of thing. You can find a full overview of all 9 of the brokers in the rubinobservatory.org website. We call 7 of the brokers full stream because they take the full LSST alert stream and process it. And then 2 are downstream because they don't need all of the alerts. They have a particular science focus and so only need the alerts that are, relevant to that broker's functionality or science goals. And today it's going to be the SNAPS broker, which works with solar system alerts. So now I'm going to hand it over to David Trilling and the SNAPS broker team to take it from here.
Thank you, Melissa. Thanks everyone for coming this morning and future viewers on the recording. Let me share up here. Okay, I'm going to show you some Google Slides here for a few minutes. So I'll go to full screen and then I'll come back out and do a live demo with our webpage. So let me organize that. Slideshow. Okay. All right, thanks. So I'm going to talk to you this morning about SNAPS, the Solar System Notification Alert Processing System. I'm David Trilling from Northern Arizona University in beautiful Flagstaff, Arizona. Listed on the bottom here is our team of people who've been working on this project collectively for many years now. Mike Gowanlock is on this call. He's co-PI from our computer science department. The names in red here are students who have worked on this, undergraduate, master's, and PhD students. And I'll also call out students from NAU's Visual Design Lab here on campus, which designed this beautiful new logo for us. Okay, I'm going to just briefly talk about SNAPS, and then I'll get into this web portal demo thing. What is SNAPS? SNAPS is a downstream broker that is dedicated to solar system science. Our goals are the following. We ingest alert data for moving objects. We derive various properties like colors and light curves. We identify individual and population outliers. We serve this data to the community via web page, outgoing alert stream, and API, and we do science related to small bodies. This morning, I'm not going to talk about our science and only talk about some of the other parts, but some of the critical infrastructure things that I want people to know about. Okay, on this call, probably almost everybody knows this story, but I just want to say it anyway. The brief review of the LSST data flow. So there's a telescope in Chile. It takes an image of the sky, obtains an image of the sky every 30 seconds. There's a huge amount of software infrastructure that goes into this game of transient detection, but we're just going to say that it happens here. And the next thing that happens is the question is asked, is the transient that was just detected a known solar system object? That's binary, yes or no. If the answer is no, then this transient, which is sent in the form of an alert packet, is delivered to brokers, including Antares. And I mention Antares for a reason here. I'll tell you in just a moment. But all of the full brokers that Melissa mentioned are listening to this alert stream. Okay, great. If you are a known solar system object, then you have a slightly different path. You get reported to the Minor Planet Center, as Melissa said. You also get reported to brokers, including Antares. And I've drawn this as kind of a pass-through because the way that we're interfaced with Antares is they receive the full broker stream, the full alert stream. And the first thing in their processing is they say, are you a known solar system? If so, go that way. And it's rebroadcast on an outgoing from Antares alert Kafka stream that contains only known solar system objects. And we are consumers of that stream, and that's why I'm shown here. Then Antares takes everybody else who's not a known solar system object, and that passes through their Antares stuff that we have heard about. So what this means is that known solar system objects are broadcast to Antares and then rebroadcast from Antares to snaps. And that's what I'll show you here today. I do want to just point out, just for completeness and understanding of what's in this ecosystem, that there could still be solar system objects here. They're just not known at the time of the transient detection. In fact, there certainly are solar system objects here, and we don't see them because they were not flagged as known solar system objects, so they don't come to us. Okay, what makes Snaps unique? We're the only solar system dedicated broker. People on this call will understand that moving objects present special challenges. I would say opportunities, pick your word. And we collect and serve moving object data, derive moving object properties, and enable moving object science. So that's really, we have a very narrow focus compared to, the whole LSST science project and compared to what other brokers are doing. Okay. What Snaps does and what Snaps does not. This, I want to just also say this, just so we're all on the same page here. What Snaps does, I've mentioned, we ingest observations, we derive properties, we have a value-added catalog, and we identify outliers. Things we do not, there are many things we do not, but I just want to emphasize here that we do not discover new solar system objects. That is happening elsewhere in the LSST ecosystem. That is a very important project, but we are not doing it. And we also are not ingesting or serving any information related to non-solar system objects. Okay. This is my only page really here to talk about Snap science and a few relevant papers here. So in 2023, we published this architecture paper and our first sort of catalog or data release, which we called Snapshot 1. I'll come back to that in a couple minutes. We had a paper led by Daniel Kramer about aliasing in period solutions, which I would say is just as much an informatics project as it is an astronomy project. Or a data science project. Mike Gowanlock had two papers, one population outliers, one about combining ZTF and test data. Maria Chernyavskaya has a forthcoming paper about super fast rotating asteroids. Aaron Clark has a forthcoming paper about active asteroids. Those are based on both of them on ZTF data. There's not sufficient LSST data yet to say a lot there. And then there's several things here under the trilling, nope. This one, forthcoming list. The webpage and API paper has been submitted to arXiv. It is sitting in the arXiv review, whatever they do, whoever's doing it. I feel sorry for them. So I was hoping now to have an arXiv code to give you here, but it'll show up in your arXiv hopefully in the next couple days. And then Snapshot 2 is a paper that's a little bit downstream from here. Finally, there's a lot of other papers, too many really to list, that are related both to astronomy and computer science, both of which are obviously critical components of this project. Okay, here's some current statistics of our SNAPS database. This was fun to put together and look at. So let's start with the top row here. This is for ZTF, which we've been listening to for many years now. The total number of observations ingested is just over 40 million observations. That's pretty cool. The total number of unique asteroids present is just over 900,000, which is a good fraction of all asteroids known in our solar system. That's pretty cool. And the total number of unique asteroids present with more than 50 observations is this 222,000 number. So that's a important threshold for us because, as you'll see later, we derive properties of asteroids. This is the value added stuff that Melissa referred to. We derive color, we derive light curve properties, and so on. But we only do this when we have 50 or more observations for an asteroid. Otherwise, we think it's a bit too sparse, and so the derived values are kind of fluctuate all over the place. So this is the number of asteroids that will show those derived properties when I show you some examples. So 200,000, that's a good number. The LSST number is, of course, is a lot lower at the moment. Eventually, it will be a lot higher. We've ingested almost 500,000 observations from LSST. The number of unique asteroids is actually quite small. And this is because, as many of you probably know, the LSST pointings so far have been not very many pointings, but the pointing is visited a number of times. So it's kind of different from the upcoming Wide, Fast, Deep survey mode. And so what that means is that a small number of asteroids are getting observed a lot. And that's what you see over here. The number of unique asteroids with more than 50 observations is almost 1,300. So it's a pretty big fraction of all that total. However, so those observations started January and mostly in February of this year. There were a couple weeks ago, a small number, rather, I should say. The January, February observations from LSST, there was a bug in the processing pipeline in which the alerts that were distributed had the wrong heliocentric and geocentric distances calculated and listed. That bug has been fixed, but the observations from before that bug fix, because they have the wrong geometries, when we ingest the alerts, they repopulate bad data into our database. And so what we've decided is we're excluding those at the moment. We have the observations ingested, but we're not serving them. The number that we are serving with more than 50 observations, this is 114, and that is since that bug fix. And of course, that's going to go, up very fast as soon as the, full survey is underway. Okay, so I'm going to exit this slideshow and do a little live demo here, and you all know how live demos work, so let's see how it goes. I'm going to talk a little bit about our current functionality. Our new public-facing URL and web page is here, and I'm going to show you that in just a minute. Let me tell you what I'm going to show you, and then I'm going to show you what I'm going to show you. So I'm going to show you these things that are here. I'm going to show you about this login. You can use our page if you're not logged in, but it's rate limited. And also, if you are logged in, you can save your recent queries and your favorites and so on. And it's good for us. It's good for you. You should create an account. I'm going to show you how to search for a ZTF object. I'm going to show you how to search for an LSST object. I'm going to demonstrate the outputs from a search: plots, data downloads, postage stamps, favorites, recent queries, and our random button. And these two caveats here. One is this one I just mentioned about the LSST alerts with the bad helio-geo values. Those are excluded. In principle, we could go back and recover those, but we haven't prioritized it at this moment. And the ZTF comments, there's something fishy with the geometry parameters. And so at the moment, we're not serving those, but that will be fixed in short order. There are no LSST comments yet. That obviously is coming. Okay, so let me do this, and now you can see my browser, and I'm just going to show you stuff. So if you go to Snaps NAU EDU, you see this splash page. Here's our logo again from our undergraduate visual design lab students. You're going to enter, and welcome to Snaps. So the first thing you see is an object search. That's great. And then there's a message here that says, you could log in for additional functionality. I'm going to do that. Guess what? I already have an account created. Here at NAU, that's pointing me out to my Google NAU account, which will then come back. Everyone's will look slightly different there. But anyway, you come back and you're back to the same page, but now I have more stuff, more functions available for me. Okay, so the main thing here is the object search, and I'm just going to start with that. I have my notes on the other tab, so I'm just going to toggle back and forth here. So here's my examples. Guess what? We're going to search on asteroid 1, 2, 3, 4, 5. The asteroid we search on most often in our SNAPS database. So one thing to note already is that we have this string completion here. So there's a small number of suggestions you get if you're looking for an asteroid and you're not totally sure, or it'll help you just find where you're going. I happen to know this number. I've got it memorized. Okay, I search on this object. So this is our main results page. I'm going to show you what's on this page, top to bottom, then I'll come back to the top and show you some details about what's on this page. So the first thing you have is the observational record, which is time versus absolute magnitude. We have a light curve for this object. We have a Loam-Scargill panel. I'll come back to this, of course. We have a phase curve for this object. We have derived data and MPC data. And finally, an observational record down at the bottom. Okay, so let me go to the top and I'll just show you that again, one at a time. This is our observational data, Julian date here on the bottom, and absolute magnitude, not apparent magnitude, but absolute magnitude here. Apparent magnitude is at the bottom, and we'll get there. All of these panels are little Plotly tools, and so you can do stuff. There's little icons here that'll teach you what to do. You can hover over a data point and you can get from that measurement, I can tell you the Julian date, the H magnitude or absolute magnitude for that measurement, as well as the time. And so if you wanted to browse around because you thought something interesting happened on February 2nd, 2020, something interesting other than a global pandemic, you could click on this guy and you would get some information. Okay. These are, as I said, these are interactive. One thing we often use is this kind of data select tool. So then you can zoom in and see if there's any particular thing you're interested in. You can continue to zoom in. And then if you're all done with that, you can click the house and you'll go back to the original set. Okay, we're showing, of course, G-band and R-band data here. This will look slightly different when I show you LSST. Okay, the next plot down is the light curve. So what we've done here is and I'll show you this in a moment, we take these measurements and we calculate the absolute magnitude H in the G-band, and we take these measurements and calculate the absolute magnitude H in the R-band. From those two numbers, we calculate the G minus our color. We then add a constant offset of the G, or subtract, actually, a constant offset from the G-band data so that in this plot, the G and R are on top of each other. Okay, so I've basically just corrected for the color so that all the phase data will sit on top of each other so that we can look at a light curve with all the data combined. This is phased to what we think is the best period for this object. You don't have to like that period. That's totally fine. This is what's in our database as the best period. Now, I do want to point out for every asteroid for which we have 50 or more observations, we force a solution for a light curve. Many of them are good, some of them are bad. And so we're working on a metric that will express the fidelity of how good we think those solutions are. But you always will get, in a 50 or more case, you'll always get a light curve here. But I would encourage you to look at the light curve and decide if that's really the one that you like or not. One tool you can use for that is you can turn on and off some of the data and the model. So I find this useful for the light curve because you can kind of, if you have the sine curve, you're like, oh, okay, pretty good. But if you turn off the model, you might ask yourself, well, could I just fit a straight line through those? And basically it's a flat light curve, in which case the amplitude you would say is quite low and the period is basically undetermined. So again, users should feel empowered to do some examination there. Okay, so this caption tells you that period that we have fit to, 2.8 hours, and it tells you that we've shifted all the data that's not in the R band by its color. Okay, scrolling down, let's say you don't like that period. That's fine. You could run your own Loam-Scargill analysis of those data here. It runs here in your browser. Default here is you can search a million frequencies from 1 hour. These are in hours, 1 hour period to 50-hour period. You can change those numbers if you like. Those are the defaults that we set. This runs in something like under a second. That's pretty cool. Of course, if you use more frequencies, it'll take longer. And what you get is a periodogram, and then the data folded to whatever the period is. So it comes back this tool says, oh, I'm going to pick the peak out of periodogram, which is the same 2.9, 2.79. So this data is the same as what we had above. But this also is interactive. And let's say I wanted, I really thought this peak was the right peak. I'm hovering over it. I see that it tells me your coordinate. The X value is the period that we found, and the Y value is the power. So 10.86. I'm going to click there, and it populates into this bar. I'm going to apply the period. And then here's my data rephased to that new period. I think that's really not a very good fit. The periodogram power is pretty low. That all kind of makes sense. That's not a good fit. But you can really play around here, and you can search a different period range as you like, and so on. Okay, moving on, we have this phase curve panel. This is phase angle in degrees and reduced magnitude. I think that looks pretty good. I'm pretty happy with that for this asteroid. You will see examples that are good, and you will see examples that are not good. And again, you can turn these fits on and off as you like. What this means is that we're deriving in the Bowl system the H value in each band and also the G slope parameter in each band. Okay, so now we have derived data over in this panel here. Here's my absolute magnitude in R band. Here's my slope parameter in R band that I just mentioned. Here's a G minus R color, which I mentioned before, rotation period in hours, and the light curve amplitude in magnitudes. Over on the right side is MPC data. For ZTF data, these are extracted from from the MPC. Yes, that's correct. Here I have an H, but this is H sub V. It's the MPC H value. Here's how I calculated our H magnitude in R band. So those are not probably going to be the same in most cases. We have orbital elements here, and again, that H magnitude. And then finally, here's the observational data. There's 71 rows here. And this is pretty self-explanatory. Julian date, here's time if you're a human and want to read it that way. Filter information. This is now apparent magnitude, and the uncertainty on that. Those are from the alert packet for that individual measurement. For ZTF, we extract and in some cases calculate the observed distance, the phase angle, and the heliocentric distance from the time of the observation. For LSST, those are included in the alert packet, and we extract it that way. Here's the H magnitude that we calculate for each observation, and that's what allows us to build the light curve that's above. And then this thing here is a ZTF string that corresponds to that observation. Okay, let me go back up to the top. That's what's on our main page here. And let me show you a couple other things. So in this search bar up here, we have 4 different buttons that are all ZTF, and those labels are coming. They didn't quite make it for today. Snapshot 2 is not published yet. Let me show you all. So as a reminder, asteroid 1, 2, 3, 4, 5 has basically 2 epochs here in the snapshot 1 data collection. If we look in the all data collection, which is from the beginning of ZTF to today, last night, you can see that we actually have 4 epochs. And so that is a bigger data set. Everything else is basically the same here. I think the light curve fit got worse when we included more data. If I turn off the model, I personally would just draw a straight line through all those and say there's no detectable amplitude there. But again, a reminder that in our collection, we force a solution for every asteroid that has a period more observations than 50. And so you should be thoughtful about what light curves you think are appropriate. Again, the phase curves look pretty good. And now we have 217 rows in our observational record. Previously, it was 71 or whatever it was. Okay, let me see what I've got here. I'm going to show you the provisional database. So at the moment, we have a collection for, these other ones I showed you are for numbered objects. This provisional is for unnumbered objects or ones with provisional or preliminary designations. And 2015 TA 105 was the one that I picked.
David, you've got a hand up from Matt Holman.
Okay, great. I don't see that, but I'm happy to hear it. Matt, what you got?
Hey, this is great, David. A question about the light curve model. Does that incorporate light time?
Yes.
Yeah.
I think, ask your question again. I think I understood it,
Well, I mean so does it incorporate the light travel time so that
Yes,
we
it does.
okay.
It does. Yep.
So when you fold that together, it's
It's done the right way. Yes. Good
okay. So
question.
you expect it to fold together, but it didn't.
I do, and I'll show you some other ones where it looks better than 1, 2, 3, 4, 5.
Okay, thanks.
Yeah. Thanks, Matt. Um, okay, so here's the provisional. Again, these are for unnumbered objects. This one, I just picked it this morning. And I just wanted to show you, here's an object that has only whatever it is, 10-ish or so observations. What happens in that case? We have no light curve solution posted because we don't have 50 or more. We have no phase curve posted because we don't have 50 or more. We don't have derived data. Earlier today, we did have MPC data. I'm not sure why that's missing, but that should be there. And then we have the observational record, which shows you only the 10 rows. And so the collection is complete. It's just not very rich. And so we don't have those derived properties. Okay. Let's see what I've got next. I'm going to show you some LSST data. So I'll go back home, and I'm going to now query an LSST. And the object I'm going to query, this is just, again, one of our test objects that we've picked out, is this one, 16472. Now, this long string is going to disappear shortly. That is not a useful, consumable value for any person I know, but it refers to a specific LSST observation. But it has the asteroid number here at the end. So I know it's the right one. And it also happens to be asteroid 1990 OE5. Okay. And this is one of those cases from LSST where the asteroid has been observed more than 50 times, so we're ready to do stuff. So the first thing you notice is that our observations now, we have observations in 5 bands. And they're each color-coded. This is pretty cool. Now we're LSST and we don't have any Y-band measurements for this object, but in principle we could. The scale here is actually pretty large because, of course, the U-band observations are quite faint relative to the other ones, but you still can hover and you can get the information. You still can, let's zoom in on those guys. You can get just those observations. This is a very bright object, and so there are error bars here, but they're hard to see. You might have to keep zooming in until you see them, but there they are. And then you can go back home to see the whole thing. Okay, because there's 50 or more observations, we can phase this data and produce a light curve. And that's what's shown here. I think that looks pretty good. 28 hours. I don't, you could quibble with it, but I think that phasing looks pretty good. If you turn off the model, I still see the light curve with my eye. So that seems, I don't have a big problem with that. But the phase curves, and I think I mentioned this before, the phase curves are not great because our phase coverage with LSST is not very good right now because the observations have been so sporadic that we have not observed basically any asteroids at a wide range of phase angles. And so that means you're just fitting this HG business with a very small phase angle, and it's easy to get the slope wrong. And so you might notice, for example, here that these two curves are crossing each other. This is the R and the I curves. They probably don't really cross each other. And when we have more measurements at wider phase angles, then we'll have a better determination. What that results in is that over here on the derived data is that the color here, the R minus I color that we derive right now is negative. Well, I don't think it really is. I think it's just because we don't have good phase coverage. So on derived data, on the ZTF side, we had H sub R, G sub R, and a G minus R color. That was it. But with LSST, we now have a U minus R color, an R minus I color, R minus Z color. We don't have R minus Y because there's no Y observations at this asteroid yet, but eventually there will be some, I assume, and then we'll have a color here. And again, rotation period and hours and amplitude here. The MPC data, as I mentioned, is extracted directly from the LSST alert. So this is all fine. And then our observational data, 60 rows here. And again, the filters here are now listing for these observations. We have more choices for LSST. And over here on the side, you see this other designation. Okay. Let me go to the top here. And again, query LSST. And I'll just show you that you also can query on that provisional designation, 1990 OE5. Here's the same object again. So on LSST, those queries were built slightly differently. We're going to eventually merge these so that it is more seamless for the user. You just type in your object in any name that you've got, and there will be a select where you could say show me ZTF or LSST or all the data, and then we'll merge everything we've got and present that to you. That's coming in the future. Okay, let me go back to my list here. Plots, data downloads. I did not show you postage stamps. Let me go this way. So because I'm logged in, my recent queries are logged here, and I can say, oh, 1, 2, 3, 4, 5. I can just press search again. I'm back to where I was. In this case, I remembered what I was doing, but if it's been a long time and you don't quite remember, that's fine. And in this panel, here's my postage stamps tab. So this takes me to my, and that's also directly accessible on the left side here. Here's postage stamps for asteroid 1, 2, 3, 4, 5. So as Melissa mentioned at the beginning, alerts or transient objects are packaged up into an alert that has 3 little cutouts. There's a science image, a template image, which is an image of that piece of sky from some previous time, or really a median image from some set of previous times, and the difference. So science minus template equals difference. So here's our asteroid right in the middle. You can see the template has some field stars. They're sort of apparent in this science image, and then they're missing in the difference image, and the only thing in the difference image should be the asteroid. There's a little bit of interactivity in these little widgets, but it's not great. But you can download each of these with this arrow. These come in little fits files that will show up. You can scroll over here, any other postage stamp you want. Let's say you thought this asteroid did something interesting on May 23rd, 2025. I'm going to go look at it. No, not that interesting. Oh, maybe this one. Oh, I don't know. So you can scroll around in here, or if you want the entire stack of postage stamps, there's a download here, and that'll package up all of the set, each 3 little cutouts for the entire time series that you've got. Okay, I'm going to go back here, and I'm going to again search on 1, 2, 3, 4, 5. And obviously, this is my favorite asteroid. I'm going to star it. So now it's my favorite asteroid. And I can go over here on the side for faves. And this is, maybe you've got a small number or a large number of asteroids that you want to just continue to ask about. You don't have to type all that stuff. It'll just be a series of favorites here over on the side. And you can just go there. And if you click on it, it takes you back to that search. Okay, so that's just a shortcut for you. And you might even add some notes. Wow, neat. That's a neat asteroid. Save, and now I have my notes here. And so you could put notes like, I looked at this on April 30th, come back in 2 weeks. You could put any notes you wanted there. And of course, this is, private for your workspace. And so if you have something that you're chasing down, you can put a lot of information there. If I'm sick and tired of that one, I can just remove it. My favorites are gone. Okay, I think the last thing I wanted to show, oh yeah, so favorites would show here, recent queries are here. We at the moment don't have an outgoing alert stream, but when we do, that will show over here. And I just wanted to finally show you our random button, which will go to our database and choose a random object. And you often get ones that look like this, which is really, I would say, not very interesting. But sometimes you get something, oh, okay, I don't know what that is. Not enough measurements to have a light curve. I'm going to try just one more time. I told myself I would only press the button 3 times during this live demo. Okay, not very interesting. Let me show you. Earlier today, I was pressing the random button just to see what would happen, and I stumbled on this one. Really, this was random, I promise you. Let's go into the all query so we can see all of the ZTF data. And I don't know what's happening here, but this asteroid got 1.5 magnitudes fainter and then recovered. And the G band and the R band are, has kind of parallel tracks there. And also there's a measurement, okay, a very bright measurement you could imagine got corrupted somehow, and we could go look at the postage stamp. I haven't done any analysis on this. It just popped up in the random, and I thought, well, what on earth is going on? We, of course, do force a light curve solution. That one's not too bad, actually. There's this faint point outlier and a couple bright outliers, 218 hours. Okay, that's pretty interesting. And then another one that I found in my random search this morning, again, just by pressing the random button, was this one. And again, some data points that are really, there's a lot of scatter all over the map here, which is kind of more than I would expect to see. And that light curve to me looks like junk. We clearly have not fit this light curve correctly. You know, all those points are missed, all these are missed. So this is a case where if I was interested in this asteroid, I would go poke around in my Lomscargel. I might down select some of this data and maybe see, is that what that's telling me? Here's this another asteroid that has this big brightness decrease in the G band and an increase in the R band that are almost at the same time. I don't know what that is. This happens to us all the time, that we're just clicking around and we think, oh, there's another completely bizarre asteroid. So, you know, the conclusion of that is that the asteroid belt is way more interesting than I think we understood, but we haven't yet had a comprehensive survey of this scale that we really could understand it before. So I don't know. I don't know what to say about those asteroids, but they look interesting to me. Okay, I covered all of those things. So let me just finish up here. I did cover that. I'll go back to this and just finish with a couple bullets coming soon. Let me talk about our API. So we have an internal API that is functional, and all of the stuff I showed you was kind of like, look at your favorite asteroid or 3 or 5 or 10. But if you wanted some kind of bulk query, like show me all the postage stamps from that night, or show me, give me all the light curve periods for every asteroid in this semi-major axis range, or something like that. That's an API kind of query. That is, I would say, mostly functional internally, and it will be externally facing and available for community use. Coming soon, I'm going to call it months. So like summer. The other thing that we're underway towards summer is the LSST community filters that were provided last year, whenever that was. Solar System Science collaboration developed 3 priority filters, which are basically summarized here. One is a search for activity based on photometric variability. One is a search for activity based on PSF anomalies, and another is a search for individual outliers that could be unusual in either photometry or in color. And we basically have all of the algorithms for those completely built. We have not totally translated them into the kind of filter that was proposed and requested. And so that's coming soon, is basically to take our algorithm and package it in a way that we can then serve alerts based on these filters as well as ones that we're developing. So that leads me to this future feature, which is an outgoing alert stream. It will be a Kafka stream that emanates from, that we broadcast from snaps. It will again contain the alert packet information, including those postage stamps and the value add stuff. And additionally, it will say, why do we think this is an interesting object? I don't want to tell you about 222,000 asteroids every night, but an individual one that we think might show signs of activity, and here's our evidence for it, all contained within the alert packet. That will be an outgoing alert. And also population outliers, objects whose properties we think are intrinsically unusual compared to the rest of their population, those also will go in an outgoing alert. So if you are interested in unusual asteroids, if you have a telescope that might be used to follow up in unusual asteroids, you can consume that alert stream that we're sending you. And inside you can say, well, I only want activity. I don't want this. I don't want that. And then you can down select and act as you like from there. Okay, so here's my last page. Our Snaps webpage is open for business. There's the URL. The documentation is available in quotes, so it's submitted to the archive, but we're in this like archive limbo thing where they haven't yet assigned us a number. I was hoping there'd be a number this morning, but anyway, coming soon to the archive near you. Additional features are coming. Just to, be completely clear about this, this will never be perfect, but we've come a really long way, and our team has been really tremendous, and I thank you to all of you, anybody from our team who's been participating. Feedback is welcome, either directly to me, to our team members, or we have a contact form on our webpage. You can send us messages that way. And I would say enjoy and happy sciencing. Thank you.
That was excellent. Thank you, David. We've got time for questions, so we can do hands up and we'll go through people and invite you to unmute, but let's start in the chat because I can see some questions starting around 9:30 if you want to address those in turn.
Yes. Cassandra, hi. Can you force a light curve analysis in the browser if there are less than 50 observations? So let me share back. The beauty of the live demo is that if I don't know the answer, we can just try it. So here, let's do it the fun way. Let's go snapshot one, random. Chances are good we'll get a very sparse observation record. Darn, we got a good one. Let me try one more and then I'll go to the one I know. Okay, 2 measurements. Let's try to force a light curve. The answer is yes. In this particular case, that's obviously completely garbage, but if we had, let's say, 25 or 30 or 35 measurements, there would be something useful there. And it might be a perfectly good solution that we just haven't come to yet. That's a good question. Thank you. Let's see what else is in the chat. Will you be ingesting data from other databases? Okay. Yes. So we have a hook for Atlas data, which we're not presently serving, but we do have it sitting in our collections. In the future, we're looking at Argus, which I think would be a fairly substantial but straightforward task because it looks a lot like the kind of data that we're ingesting. We also have a hook for test data that we're also not yet serving, but it's sitting around. So the answer is yes. There's a little bit of a trade-off about how much work versus what's the utility. Those all would be useful. There's a question about how much work it is to make them kind of play well with what we're already serving. But the answer is yes and yes some more. How about that? And then Tim said, is there documentation for the outgoing alert stream format available yet? There is not. I have in my mind, I can imagine what it looks like, but there's no documentation yet. Good question. Colin, go ahead.
I'll follow up to Tim's question then. If there isn't documentation, but you have an idea, can you roughly describe what you think the outgoing alert stream looks like?
Well, on a concept level, yes. And I tried to say this before, but basically, let's imagine there's an asteroid observation that comes from LSST. Our algorithms say this one looks like it's active because it has a beautiful tail or it has a very fat PSF or something. We flag that in our algorithms. We then, as soon as we can, which should be quite prompt, our algorithms, those tools that we have in-house run in less than 30 seconds. And so it's from the first set of alerts for an image to the next image, a set of alerts. During that time, we've done that analysis. So I don't know exactly how long it will take to populate the outgoing alert stream, but it's very fast. That image comes to you, you're a subscriber, you're a listener, and you see what we see, which is the science image, the template image, the difference image. You see all the data and metadata in the original LSST alert packet. And then you see our value add, where we're going to tell you everything we know about that asteroid. I'll tell you the period I derived, I'll tell you the color we derived, and all that other stuff. And then another thing which you don't see here yet, which is the output of those activity filters or activity detecting algorithms, which will say, we think we see a tail in the image, or we think this PSF is unusually extended compared to other PSFs in the image, or something like that. And our intention at the moment, we have a, let's say, not perfectly mature probability statistic that we can label each of those. So we think we see a tail, 70% chance that we see a tail in this image. Okay. If I gave you a 95% chance, you probably would go with your telescope and chase that one. If I gave you a 20% chance, we won't report 20s. We only report above 50 probably. But if I give you a 51% chance, you might not spend telescope time on that until we all have trained each other on basically our confidence on those. Same with the PSF stuff. So the idea is that the outgoing alerts from us will have some confidence that we will establish and report, in some documentation about how do we establish it. Does
Yeah.
that help, Colin?
Yeah. But I mean, is this going to be like a Kafka stream or something
Yes.
in practical
Yes.
terms? Yeah. Okay.
Yes, exactly. It'll be the structure will be basically exactly the same as the LSST alert packets or an alert stream, but we add some additional stuff at the bottom with this results of the metrics and the filters that we've implemented.
Okay, thanks.
Jamie, go ahead.
Hi, David. Thanks. This is all really cool. I was just wondering because this is something I've been thinking about recently as well. Is Snaps using any particular flux for like which flux measurement is used and which is most useful for making the light curve, for example? Because I've been playing around with this and trying to see like should we be using PSF flux, trail flux, aperture flux? I was just wondering if you had any insight on that.
Yeah, so I sort of know the answer and the rest is buried in our documentation. But for example, with ZTF, we're using this field that is called MagPSF and SIGMAGPSF. Those are exactly the fields that we're using from the alert packets. And for LSST, I'm not certain that we have populated that correctly. Let me just check. MagPS. I'm not certain those are the same keywords with LSST. So I might have to get back with you on that. But it's written down, and I don't have the answer offhand.
Okay, cool. No, thank you very much.
Yeah, good question. Thanks. Yeah, go ahead, Mike.
Hey, David, is similarly, or well, is there a way to assess the trailing of a source in this interface?
I don't have a way to share that with you other than I guess you could look at the postage stamps, which is a pretty,
Yeah.
like for one or two objects you could do it, but I don't have an algorithmic way or a database way that we represent that here.
Okay. Because I was thinking about the particular one of the light curves you showed where there seemed to be a big dip.
Mhm.
One of the things that came to mind, well, maybe it's just close to the Earth and the photometry isn't well fit by a PSF, whatever.
Yeah,
Okay.
that's a good point. And if that was your favorite asteroid, we would probably go look at the postage stamps and we would kind of, on a one-by-one basis, that is the tools we have are doable, but
Sure.
on a more algorithmic basis, we don't have that set up for that to answer that question.
Yeah.
I will say that, sorry, go ahead, Mike.
Oh, no, go ahead. You go ahead.
We have very few NEOs in our database, and that's because there are not many NEOs that reach this 50 or more observations threshold. Sorry, we might have 2 or 3 or 4 observations. They're in our database, and you could query them, but we don't have derived properties for those. And that is because of the apparitions of NEOs, it's hard to get over the 50 or more observations. There are some, and we've presented some in a couple papers, but the consequence of that is that, Mike, if you see one that has 50 or 100 or 200 observations, it's probably a main belter. It's probably not an NEO.
Yeah. Well, at the same time, the real bogus probably prevented significantly streaked objects from going through the ZTF alert stream anyway.
I'm glad you mentioned that. So we are now above the real bogus cut. So we have observations with any possible real bogus score, for better and for worse. But for a while we were limited. We were too far downstream, and so we only got real bogus alerts with real bogus scores above 0.6 or 0.55 or something like that. And so that threw out extended objects. It threw out trailed objects. Okay, trailed, maybe that's fine, but extended objects that look like comets, some people might be interested in that. So we've been able to move up that we now have real bogus from anywhere from 0 to 1 in our
That's good.
collection.
That's good. So whatever cuts ZTF has, that didn't change as I understand, because I don't remember that changing.
So the thing that changed for us is that we used to be farther downstream in Antares, and they had a real bogus cut above us.
Okay, got it.
We've been able to engineer that with them, that it's now switched. And so the first thing they do is they get rid of solar system by sending it to us, which makes everybody happy. And then they can do what they do and we can do what we do.
All right, thanks.
Yeah, thank you. Madeline, go ahead.
Hi, that was really interesting. Thank you. Just following up on that question, do you know if that differs to other brokers? Are the other brokers all only receiving ones above a certain threshold, but you've now got access to all of them?
I'm sorry, I don't know the answer to that.
That's
I don't
fine.
know. Melissa, is that something you might know, or is that?
I think they are right now. The outgoing stream has a real bogus threshold that is higher than was the plan to keep lots of junk out for now.
Oh, I see.
Yeah, until they can calibrate the real bogus and then lower that number. But I don't remember what the number is. So I think all the brokers get the same thing though right now.
That makes sense. Thank
Yeah.
you.
All right, more questions for David, either with hands raised or in the chat. I'm just gonna stop